colleagues. Okay, so it's now 10 minutes past 5 here in Moscow, and I'm very happy to announce our talk. A great friend of ours, Lou Kauffman, will give us a talk about relations between graph colorings and virtual colorings and virtual links and back. So let's welcome.
Thank you, Vasily. It's a pleasure to be talking with you. Let me share the screen here and we'll, let's see, you have to give me permission.
Just a moment. I think you do have it.
No, it says host disabled participants.
Just a moment. It's I think it's not me who gives not me. I'm not moderating this. So please give the permission to Lou. Please give the
please try again.
Okay. There we go. All right. I often begin talks about virtual knot theory with optical illusions, so I wanted to do that here as well. This is the famous Knizia illusion, which you probably are familiar with. You may not be familiar with the sequel to it that I'm about to show you. In the Knizia illusion, what's actually drawn are three deleted black circles and three deleted three angles, but your mind, usually my mind, probably your mind, constructs a big white triangle in the middle that seems to be quite whole and uniform with imaginary boundaries delineated for you. They're there. Someone, I don't remember where I got this, had the idea, could we make a Knizia illusion that would produce a tetrahedron instead of a triangle? And they solved it this way. And if you stare at that for a bit, indeed, a tetrahedron in the middle should now be hovering in your mind's eye, right there. That's quite remarkable. Extra virtuality produced by what? Well, worth thinking about. Okay, so that's I'll leave that for a moment for you to look at. If you're interested, I'll send that along with slideshow.
Yes, please.
Now, here's the slides. Whoops, we got to get back to the beginning. Okay, and let me set it up so you can see the whole thing. There, all right, I hope that's quite visible to you. This talk is self-contained and somehow wants to go on its own. Talk is self-contained, and it's entitled From Colorings to Virtual Links and Back. And this is a project of mine which goes along in parallel with some joint work that you may have seen of mine with Scott Baldridge and Ben McCarthy and William Rushworth, where we talk about certain categories of graphs called graphenes, and we go back and forth between certain kinds of polynomials, which are called perfect matching polynomials, and virtual knot theory. But this is self-contained, and as I say, it goes in parallel to that project and goes in a somewhat different form. You'll see what the difference is as we talk. So I want you to, so some of this is recollection if you've heard me talk about it before, but I think the talk is self-contained. Recall the problem of three coloring the edges of a cubic graph. So here is a cubic graph at the bottom of the slide, and we have three colors, A, B, and C. And the puzzle is to put three distinct colors at every vertex. And the problem is solved for you for this graph that you're looking at. You can check. that at every vertex A, B, and C occur? I hope. Yes. Very good. So that's the problem. That's a nice combinatorial problem. And it turns out that this problem is related to the four-color theorem for maps or graphs. You recall that in the four-color situation, it started with maps, regions, coloring regions so that adjacent regions were colored differently. And then it ends up being reformulated in terms of coloring the vertices of a graph so that if they're connected by an edge, they're colored differently. But I want to explain immediately what the relationship is here between coloring the regions of our cubic graph in the plane and coloring its edges. And the relationship is what's often called the Klein foregroup, Z2 direct sum Z2, with generators and relations W and identity and A, B, and C, so that A times B is C, B times A is C, A squared, B squared, and C squared are W, and in fact, the product of any two of them, that's that little circle that I drew there with an arrow, cyclically permute. B times C is A, C times A is B. All right. And then this gives you a way to multiply colors, four colors, W, A, B, and C. If you have regions and you have a colored region and another colored regions, then you take the product of the region colorings and get an edge coloring. So as you see, if I started with if I put down region colorings here, then you see that I'm getting the edge coloring from the region coloring. W times A is little A times B is little c, A times W is A, W times C is C, and so on, so that the region coloring that you see in the right-hand corner and the edge coloring are in one-to-one correspondence with each other. And of course, you can go back and forth between them. If you have a region coloring, you can get an edge coloring. If you have an edge coloring, you can get at least one region coloring, and always more, in fact. So the four-color theorem says that a cubic one-connected planar graph, one connected means there's no edge which will disconnect it if you remove that edge. A cubic one-connected planar graph can be colored in its regions with four colors, distinct across region boundaries, and that's equivalent to saying that it can be edge three-colored. So that puts our problem in context, and I want to remind you of some other matters about this, because at the beginning of this talk, and for quite a while, we're going to be thinking about the coloring problem, and then we're going to start transmuting it until we find ourselves in virtual knot theory. You'll see. So another piece of background that's important is, suppose you have a coloring and choose one of the colored edges in that coloring and mark them all. And then you are looking at a perfect matching on that graph. You have a collection of edges which comprises all of the nodes in the graph and are disjoint from one another. That is a perfect matching by definition. And this perfect matching is special in that every cycle in the complement of the perfect matching edges is an even cycle. That's because every cycle is alternately labeled by A and B, the other two colors. For example, I've illustrated it here. There's only one cycle in the complement of the three perfect matching edges. And as we walk along that cycle, we alternate A, B, A, B, A, B, and come back to where we started. Since we can alternate, there are an even number of edges in that cycle. So therefore, when you have a coloring, it gives you an even perfect matching for the graph. And conversely, if you should give me an even perfect matching for the graph, then I can color it by using one of the colors for the perfect matching edges and alternating colors on the cycles in the complement. So another way to search for the holy grail of proving or giving a new proof of the four-color theorem is to look for perfect matchings that are even, or try to show that every non-even perfect matching can be transformed to one that's even. Now I want to formulate this another way. Consider that we will call the colors red, blue, and purple, and think of purple as a combination of red and blue. C is now a combination of red and blue. Then I can reconfigure my graph by using that coloring that way, and you see that you go along A in red, and then you continue in red along C because it's a combination of red and blue, and then you continue along A in red, and then you continue along C, and you get a red cycle. It's drawn here, nice red cycle, which goes through A and C, and you have a blue cycle which goes through B and C, and in general you'll have many blue cycles and many red cycles, and I call that a formation if the red cycles and the blue cycles interact in these forms that I'm showing you over here in the middle of the slide. That is, a blue cycle comes along, shares a bit of blue with a bit of red, forming an edge, and comes off. And it can come off either to the left or to the right of where it started, and it could just go backward along the same side of the red curve, or it could cross the red curve. So that is the definition of a formation. A formation is something you can draw at will. Just make some formations by taking two colors and drawing them. And every time you do, you will have colored some underlying graph of that formation. And the underlying graph consists of the combined color edges, the red edges, and the blue edges. So we have this kind of picture. I might have drawn this formation at the top, but once I've drawn it, I can carefully delineate where the nodes are and draw a graph and write down what coloring of the graph I had produced. And if I have a graph, I can obtain a formation. Colored graph, I can obtain a formation from it. So now the four-color theorem says that every one connected planar G can be formated. And that's the background on coloring. And now we're going to think about the Penrose formula. Now, but this is the Penrose formula here on this slide. Penrose formula takes the form of a kind of skein relation for graphs that says that if you have two adjacent nodes sharing an edge, then you can smooth them, getting rid of both nodes, or you can smooth them in a different way, which we call crossing them.
By the way, have you ever thought about any possible connections to Fox colorings?
Yes, I could, but I have even done that exercise a number of times, comparing one to the other. But this seems to be distinct from Fox colorings, and it would be a sort of side talk to explain how it's related. Let me give you an exercise. Try combining in a category of trivalent graphs that also includes not crossings. Try combining Fox coloring with this coloring and see what happens. Okay?
Okay.
But let's not go there right now. We are going to get to some knot theory very soon. So I put a virtual crossing in here. And the reason I put a virtual crossing in here is because from the graph theoretic point of view, this is a virtual crossing. When you're thinking about colorings, this could be colored red and that could be colored blue, and they don't interfere with one another or mean anything. The only stipulation is that as you go along a line, it's constantly colored. And otherwise, these crossings in the diagrams we produce, in the diagrams in the form of this skein expansion, behave like virtual crossings. Two of them together in a two move go away. You can remove a one. You can do the third move. You can push one naturally across a vertex. They're just there to indicate connection. And the value of a loop is 3. So now you know how to compute the number of colorings of a cubic plane graph by using this recursion. That's Penrose's theorem. Penrose's theorem is that if you compute using these relations, you get the exact number of 3 colorings of the graph. Let's look. Here is what I call the dumbbell, and it has one edge, and when you expand that edge and cross it, according to Penrose's formula, you get 3 minus 3, 0. And indeed, there is no coloring of the dumbbell. The dumbbell is an example of a one-connected graph. You remove that edge and it falls apart. Here's a legitimate graph for coloring, a theta graph. And when you expand that on Penrose, you see you get 2 circles minus 1 circle. 3 squared minus 3 is 6. And indeed, you have 3 choices for the first edge, which limits you to 2 for the second and 1 for the third. And you have 6 colorings of that. So that's Penrose. Now we need to prove it. And on this slide is the summary of part of the proof. First of all, the identity that we were using, the skein identity, is a tensor identity for a certain tensor, which Penrose uses to make his definition. So Penrose's definition is that you make a tensor net from the graph. That is, you're going to put a diagrammatic tensor at every node of the graph. And the diagrammatic tensor that we use is the square root of minus 1 times epsilon ijk, where ijk is the clockwise cyclic order at the vertex of indices placed on that vertex. Epsilon ijk is 0 if any 2 of its indices are equal, and it's equal to the sign of the permutation ijk of 1, 2, 3, or ABC. Otherwise, so you see epsilon 1, 2, 3 is 1, but epsilon 2, 1, 3 is minus 1. And I say you take the tensor contraction of the tensor network that you produce. That means that you sum over all possibilities for the indices the products of the weights at the vertices. That's the tensor contraction of the network. So at every vertex, and for every choice of indices, we are going to have either plus or minus the square root of minus 1. You'll have a sum of products of plus or minus square roots of minus 1 over all index choices. Let me, excuse me.
Yes.
You have to pardon me. I have a cold, and so I keep getting hoarse. You had a question.
Yes, my question is, well, for planar graphs, everything is even or positive, and maybe there is a possibility to get not just plus or minus 1, but a sort of homological information. So a certain sum where instead of epsilons, we have something like homological homology groups of loops.
That's a possibility. I'm about to show you how to get this off the plane. So we'll see.
Okay.
But this is indeed a local index for the state sum. It's a state sum, and now I can explain to you that this expansion is a tensor identity. It's a tensor identity about the epsilon. It says that this connection of 2 epsilons summing over the middle index is equal to the product of 2 Kronecker deltas minus the cross of 2 Kronecker deltas. And I won't go into it. You've heard me talk about it before, but that's why it has the tensor, why from the tensor point of view, it has the skein relation. And on the other hand, this is the definition. It's well defined for any graph that you would write down in the plane by this method. All right. But now we have to think about the following. Oh, excuse me. Let's stay with this for a moment. How is it going to end up turning out that it counts colorings? Every one of these products of plus or minus square roots of minus 1 is going to turn out to be equal to 1 when it's a coloring. also, you'll notice that every one of these products, the only ones that contribute are colorings, because if there is any two indices equal at any vertex, it's zero. The epsilon is zero. So the only things that survive in this state sum are colorings. We're summing over all the colorings, certain products of plus and minus I. And you need to see that every product is equal to 1. To see that every product is equal to 1, you do the following. I do the following. I look at it as a formation. The coloring is a formation. And I take in the formation language the plus square root of minus 1 to be red, blue, purple in that cyclic order. That's a convention. That'll be plus. and then blue, red, purple will be minus square root of minus 1. Okay, with that convention, look at what happens in the formation. If you have a crossing, then you get a plus square root of minus 1 at one end, and you get a plus square root of minus 1 at the other end. Red, blue, purple, red, blue, purple. Therefore, you get a minus 1 that corresponds to blue crossing red, or red crossing blue. On the other hand, if there's a bounce, then you get a plus root minus 1 and a minus root minus 1, and they multiply to 1. And so when you get a bounce, you can just pull it off. It doesn't cross. You have a blue loop and a red loop. They don't cross one another. And they don't contribute. They just contribute to 1. So therefore, the product of the plus and minus i's for a given coloring is equal to minus 1 to the n, where n is the number of crossings between the red and blue curves. And of course, that is even because we're in the plane, and the number of crossings between one of my red Jordan curves and another blue Jordan curve is even.
By the way, there is a question I think I haven't asked before. So sometimes people like categorifying objects in order to get a higher dimensional things. So assume we have some cobordism between graphs in a natural sense. So we can have birth or death or saddles. Is there any good way of getting colorings for some cobordism between trivalent graphs, whatever it means?
I have to admit, I haven't thought about what will happen to the colorings under cobordisms of the graphs. So let's mark it as a question and think about it.
Thank you.
Okay, so you're clear about the proof. And once you're clear about this proof, it should be almost clear to you why Penrose's formula will not work if the graph is, if the graph is an immersion of some non-planar graph. Let's look. Here's an immersion of K33, and this is a non-planar graph, and it has a virtual crossing implicit in it in order to draw it in the plane. And we might think, well, maybe Penrose expansion still works. Let's expand it. So we expand on that upper edge, and you see we get a box, and we get a little virtual crossing that has no effect. We have a Reidemeister Two virtual crossing. We'll pull it apart, and we look at what we've got, and we've got a box in denominator form, and we've got a box in numerator form. They're exactly the same as graphs, and we have the difference between them. We don't have to count any further to say that this is 0. So Penrose formula gives us 0. But this graph has 12 colorings in the sense of coloring that I just mentioned. 3 distinct colorings per vertex. 12, not 0. So then the question is, how can you modify the Penrose formula so that it will give the correct answers for non-planar graphs that have been immersed in the plane? So what goes wrong is the sign coming from the plus or minus square root of minus 1s in the tensor contraction. Obviously that's what goes wrong, but how is it going wrong? Well, The problem is that the initial immersion crossing in the graph. We're going to change this to a new tensor and a new virtual marker. Instead of having an ordinary innocuous virtual marker, I'm going to have a square virtual marker, and the square virtual marker for the immersion crossing will say that when a coloring happens at that crossing, if the two colors are different, you get a -1. And that counts one more -1 for crossings of red and blue curves. It's obvious that this will now work. And 1 if they're equal. So that is the fix. When you have a red, and so now we have, and let's just check that it works and see how it looks combinatorially. So here's the K33, and we are going to expand it the way we did. But now notice, excuse me, I'm getting something out of the way here. Right. Now notice that we have two virtual crossings in our theory. So let's step back and ask, what kind of virtual theory are we doing with two virtual crossings? Each individual virtual crossing type acts by detour. If you have a consecutive sequence of round virtual crossings, you can cut them out and put them somewhere else. If you have a consecutive sequence of square virtual crossings, you can cut them out and put them somewhere else. They detour over one another. However, it is not the case that they are completely ignorant of one another, and there is no reduction of a Reidemeister Two move picture, which contains a circle and a square. So that's the way this virtual situation is going to work. Doubled virtual crossing theory, which we're evolving here in the graph category, but we'll soon have it topological. So let's look at the calculation now. We smoothed it here and crossed it there, and we have to keep track of this two move configuration. And now I'm going to do it again. So I'm smoothing here. And when I smooth, sorry, just a moment. Right. This guy over here on the left, I'm simplifying because, of course, a self loop goes away. I simplified it and I'll keep track of it. The one on the right, I'm expanding here and crossing here. Now, keep track. This is a double occurrence of a round virtual crossing and can be simplified. This is an occurrence of a cancelable loop and then another cancelable loop. So this term becomes ordinary, and this term simplifies to a diagram with one square crossing. Now this you can evaluate. You can check easily that this is going to give you 2 times 2 times 3. I leave it to you to check. And this one is a -6 for sure. And over here, we expand on this edge and we get this and this. Now, this term here is just a loop. So that's a 3. And so I'm getting 12 minus 6 is 6, and then I'm getting 3. And then I have this term left over here. And now, how do I evaluate this? Well, if they are both the same color, and there are 3 ways that that can happen, I have to count that. That's 3. Then the other possibility is that one is red and the other is blue, and there are 6 ways that that can happen with a minus sign. And so the value of this is 3 minus 6. And so now you add it all up and you get 12, and that's correct. So by adding in the extra sign that could have that can happen because of the immersion crossing, we get the correct count independent of how you immersed it in the plane. So you can take any graph whatsoever, cubic graph, whose coloring number you want the number of colorings for it, put it in the plane and apply this modified Penrose recursion, and it will give you the answer to the number of colorings. This obviously deserves further investigation. So thus we can now formulate a general Penrose evaluation to count the number of colorings of arbitrary cubic graphs we use an immersed representative. We take a Penrose expansion, and we use the round virtual crossings for the skein relation because those are inside and don't involve extra counts. We take the value of a basic loop to be 3, and we use the special tensor for the immersion crossings. Next, we're going to next have generalized Penrose polynomials for graphs with a perfect matching. We're going to have generalized double virtual knot theory, and we're going to have relations between them. You'll see. We can try to generalize Penrose's G to a polynomial. This is another direction of generalization. And you may have heard me talk about it before, but I'm going to do it for this new evaluator. What you can do is you could say, for example, that you will keep this expansion formula, but you'll let the loop be arbitrary and try to get a graph polynomial. And when you do that, you find out that while Penrose didn't depend on what perfect matching you chose, if you chose one, didn't depend on how you expanded it, here you will have to explain a perfect matching in order to go ahead and expand and get an answer, but it depends on what perfect matching you chose. These are not even perfect matchings you're choosing, just any perfect matching to enable the skein expansion. This is what happens. This is what we studied before. And this will happen here too, but now I want to do it for the generalized polynomial. How does this look? I now have a generalized skein expansion, x times 1 smoothing and y times the cross smoothing, a delta evaluation for a loop. But we also need how to explain how to handle stinkers like this that consist of a round and a square virtual. How did we think of this? We said if they were colored, excuse me, if they're colored the same, we count. If they're colored differently, we negative count. So this would be delta, since if they're colored the same, there's only one coloring of it. And delta times delta minus 1 is the difference count. This could have delta colorings, and then you get delta minus 1. If delta was a number and you were counting colorings, you take the difference. So you get 2 delta minus delta squared. So we want to say this in general. And the philosophy here is the philosophy for building chromatic polynomials going back to Whitney. Whitney started with the following tautology in blue up here. Any coloring, no constraint, is going to be counted as those that are the same plus those that are different. But what we want here for the square virtual is that will be equal to same minus different. And different is equal to any minus same. Therefore, it is 2 times same minus any. And I will give a new marker for same. If I put a nodal dot on a crossing, that will mean that these are same. And that means that circles that are touching with a welding dot like that will be regarded as just one entity with only one possible color, so that a welded pair of circles like this can only be colored once. Its value will be delta. If you have a combinatorial collection of circles that are connected and they all have dots on them, then the value of it will be delta. There's only one delta. It is a contraction. On the other hand, we can expand the square virtuals into contractions and ordinary virtuals, which just count the number of loops. So then we see, for example, expanding my Reidemeister Two configuration of two circles, I get two times a welded minus an ordinary one, and that's 2 delta minus delta squared. So this is how we generalize from counting colorings to producing chromatic type polynomials. So that means that you can now think of this as an expansion plus certain kind of altered chromatic evaluations of all of the different configurations of circles with virtual crossings that occur at the bottom. And that will be the Penrose polynomial generalized, and you need to choose a perfect matching to explain which crossings, which edges you will expand. If you expand on a different perfect matching, you will get a different result. And that means that this polynomial is of interest for studying immersed graphs with perfect matchings because it can distinguish various perfect matchings from other perfect matchings and is therefore an interesting gadget to think about in the graph theory. So here I've just explained again about any form of loops. For example, if you had this form of loops, you could expand it and calculate and so on. Excuse me, I'll stop talking for a moment.
Yes, and I have a question. So I have written it on the chat. Well, sometimes we pass from qualitative characteristics, like there exists something planar, for example, or there exists a coloring or something like that, to some quantitative characteristics. For example, something is planar, and we can look at the number of plane embeddings. So now I'm asking, is there any quantitative characteristics of some minor properties? By that, I mean the following. So, for example, if we know that f is planar, then any descendant of it is planar. Maybe we can arrange some nice functions which could be which could be monotonous for minor operations. I don't know monotonous in which direction, but this is the question of passing from the existence to the number. So that's my question.
I'm not sure what your question is. Let me make a remark before asking you again. It's a famous theorem by now of Robertson, Seymour, and Thomas that proved not only the four-color theorem again by their methods, but proved the Tutt conjecture. The Tutt conjecture was that if you have a non-planar colorable, then it has a Peterson minor. And that means that by deleting or contracting edges, you can get to a Peterson graph in any uncolorable. I said colorable, I meant uncolorable. If you have a non-planar uncolorable, then it has a Peterson minor, right? And this is an example of invariants under things of the kind you're talking about. There is no known elementary proof of that either, other than these complicated enumeration type proofs of the four-color theorem. They extended those kind of techniques to get the Tutt conjecture. So that's an example. Looking for a Peterson minor is an example of looking for something like that. And in general, I don't know how these new polynomials are acting with regard to questions about minors. But that's your question roughly. Do you have it more precise than that?
Maybe we can discuss for a while and have it more precisely. So the question is, we can put 0 or 1 for example, planar or non-planar, or maybe colorable or non-colorable, or something like that. 0
right.
or 1, and we know that if something is minor closed, well, we know the definition of minor closed.
Yeah.
We never,
now certainly certainly with something like colorability, it's not minor closed, but
I want to have some
but
quantity.
you're looking for properties that, and if you're thinking about generalized operations on the graphs like cobordisms, then sure.
No. I'm not asking about cobordism. I'm asking about I'm asking about quantitative characteristics. So before that, we had some characteristics like 0 or 1. It's planar or it's non-planar. And if it's planar, then any descendant is planar. And my question is it so maybe instead of saying it's planar and putting just 1, we can say, okay, it's planar and it has some number. And then I want to figure out some monotonous function, which is 0 if it's non-planar, and which, for example, equals number of plane embeddings. Well, I don't know precisely, but
well, yeah. So your question is, are there characteristics of the graphs that will be preserved under contraction and deletion?
Well, not preserved, but so an inequality, monotonous, I would say, monotonous. Yeah. So quantitative version.
Are we finding that such new properties of that kind are suggested here?
Well, I don't think. I think for that property it should be wrong, but maybe it can be something like the number of ways of doing something. For I don't know.
Okay. So again, we have to mark the question and investigate it, right? I don't have an answer for you. You don't have an answer for me, but it's a good question. Are you there? Yeah.
Sure.
Now let me get back to what I was saying here. The kind of method that I was doing here, remember, I said twice welding minus allowance, which is the same as saying twice same minus different. And if you put that language into a chromatic form for vertex evaluations, it would say twice same, where contraction means same, minus any, which is removing the edge. So that you see that this is a contraction deletion algorithm that's being performed on the residue circles of the skein expansion. Every residue set of circles is undergoing a contraction deletion algorithm in order to get the number of colorings for the general graph. And this needs to be looked at in the context of course, the Tut polynomial, which is designed to hold all possible contraction deletion algorithms. There's something to be thought about there. Now we have a generalized Penrose perfect matching polynomial like this. Here's a perfect matching edge. Here's the expansion, and at the special virtual nodes, we have this contraction deletion algorithm. And now we want to go to knot theory. And I'm going to use the same kind of association to knot theory that we used in our previous work. Trivalent double virtual graphs with perfect matching. That's what we've been talking about. I don't have a name for it. We called trivalent ordinary virtual graphs with perfect matching graphenes, but I haven't decided on a name for this. Maybe they should be called double graphenes, but you should remember what they actually are. And they're going to go over to double virtual knots and links. And double virtual knots and links means so you have two virtual crossing types, round and square, and they satisfy all the combinatorial things that we've already talked about. They're both detour available, but they interact with one another not completely. They don't completely cancel one another. They have Reidemeister moves with one another, but they don't come apart on that two move. And then, since I'm working in an unoriented category, I'm going to factor my graphs by flipes with the round virtual crossing, and I'm going to factor my virtuals with flipes at the round virtual crossing. This doesn't disturb the bracket polynomial, which is what we're about to find. But now we have it's not exactly a functor since I haven't made these into categories, but the mapping. And the mapping is to take a perfect matching edge and associate it to a crossing with a virtual crossing next to it. And if you then take that translation, you see that the perfect matching polynomial that we define becomes a bracket expansion at that crossing because of the extra virtual crossing, which undoes the cross lines. So now you're looking at a bracket evaluation with the value of the loop equal to delta, but in the context of doubled virtual knot diagrams. And that means that, for example, you could get a quite different result from a diagram like this than a diagram like this. We know, so you go right over to and you can, if you want, take a topological specialization, and then you're looking at a generalization of the bracket, which will give you invariants, topological invariants in the virtual knot category of doubled virtual knots. It still satisfies the flipe relation, just as the ordinary bracket does. But we are now in a larger category of virtual knots with two virtual crossing types. So, for example, you could examine. Let me stay with this for a moment. So this guy here has unit Jones polynomial, has unit normalized P because of the flipping. And this guy here is another matter, and I should have checked whether he was trivial or not. But one can work hard and show that there are some very interesting examples that will be not seeing this extra invariant, even though it is picking up more from its chromatic evaluations of the loop structures. It's a new invariant of these kind of virtual knots in a new category of virtual knots. So there are a lot of questions you could ask about this invariant, which of course is a special case of the graph version. And you can pull the graph version back and look at how it behaves somewhat topologically over in the graph category. There are lots of questions to ask. The original association here, without the extra chromatics, was allowing one to say, oh, there is a question?
No.
There is a Kauffman homology theory for graphenes that is over here. There's a Kauffman homology theory, and the Kauffman homology theory can be written directly, which is the way Scott Baldridge originally wrote it, or that's not in double virtual. I'm just talking about ordinary virtual. Or you can go by F and say, okay, we take the graph, we apply F to it, and then we take the Kauffman homology of the corresponding knot or link. And in that way, we generalize Scott's original construction to things that were virtual graphs to begin with on the left, and would go over to virtual Kauffman homology on the right. And all of that is still under construction, you might say, although there's a couple of papers that we would like to know more about the virtual homology of these graphs in relation to what we might know about the virtual Kauffman homology for the virtual knots. Now, I don't know if the doubled category has more structure in virtual Kauffman homology. I don't know if there's a way to get extra grading in relation to the square virtual crossings or some other construction that would amplify the virtual Grafana homology. We're getting polynomials which have a lot of extra variables here that come from graphs like the ones we saw, or extra valuations if you use the chromatic evaluation. But I don't know if that leads to new Grafana homology for this doubled virtual category. That's a question. You can, of course, go back and forth. For example, here's the K33. And here's the image of the K33 over in the virtual doubled category. And a couple of these rounds cancel, and we get a little triplet twist, and then we get one of those Reidemeister Two patterns. And now you see how this is working, because you see it is exactly this thing here that picked up the extra information about the K33's coloring, and it is exactly this thing here that will pick up extra information about the topological virtual type of this, which is no longer a trefoil knot. So there's lots of things to investigate here. So using this, we can generalize other invariants. Now, to generalize other invariants, I will lift myself away from the category modulo Fleip's and work in the general category. If I want to go away from the category involving Fleip's, modding out by Fleip's, I can do that by adding orientations to everything. If I carefully add orientations to everything, then putting a virtual on the left will end up being different from putting a virtual on the right, and this mod out can be removed, and then you get full correspondences that you can look at if you want to. But I didn't want to clutter my talk with the matter of orientations. So you see how you can go back and forth, and you can ask about the coloring problem by asking about the problems of the corresponding virtual knots and links. And you can image the full coloring problem for cubic graphs, not necessarily planar, into these virtual categories. Now, another direction of generalization then is other invariants of virtuals. For example, one can look at the arrow polynomial, which uses an oriented expansion, and then you keep track of these disoriented cusps that occur at the other smoothing, and you find that in order to get an invariant, you need that two cusps on the same side of a line should cancel, and zigzags don't cancel, and you have new variables like these. But now in the doubled category, we have many more, quote, new variables, things like this. Now you could do chromatic evaluations of them by expanding the node, or you can regard them as graphs to undergo reduction. So you get lots more pictures at the bottom, and those pictures will then reflect into various properties of the doubled virtual knots that are reflected in this generalized arrow polynomial. I'll probably tell you about it sometime, but not today. Many questions, and this is just the beginning of many things, and I'll stop there.
Okay, Elu, thank you very much for a beautiful talk. So I have left some questions on the chat, and actually maybe the main thing is how to get from qualitative characteristics to quantitative characteristics. Sometimes we say that some number is non-zero, hence something exists. We know some approaches. We know that there is an abstract theorem about the existence, but maybe then we can get similar theorems for the number. And if we can do something for the number, then possibly we can do some theorems for polynomials. And maybe there will be a polynomial analog of the Robertson-Seymour theorem. This is maybe the most general formulation of my question.
That's right. And in fact, when you go to polynomials, you are in a certain sense going to the qualitative. Even when you say, all right, it is true that the Penrose polynomial, the Penrose evaluation, the original one, counts colorings. But if you're only interested in the four color theorem, then you're only interested in whether it's 0 or 1. I mean, whether it's non-zero. You're only interested in whether it's non-zero. It's strictly that. And so it's quite possible that you could imagine someone finding a conceptual framework in which they deduce that the original Penrose evaluation for planars is non-zero, right? They don't care what the value of it is.
Yeah,
you're
actually,
looking for that kind of level of discrimination.
yes, and also I added a very beautiful paper by Dror Barnatan from the last century. I learned about SL2 Vasiliev invariants and for color theorem. So I added it on the chat. And there is so if something is non-zero, then there exists a full coloring. And actually, this is exactly what you're talking about.
Yes, that's right. And also the Penrose evaluation, which I didn't put it into slides here, but the Penrose evaluation is actually part of the structure of the SO3 Lie algebra. That identity, that double Y identity, and it is what underlies the structure of, for example, the vector cross product algebra, which is really the SO3 Lie algebra. So the four color theorem gets reformulated as a property of the vector cross product algebra, which is really reformulating it as a property of the SO3 Lie algebra. This is directly related to my old paper about vector cross product reformulation and to Dror's paper about Lie algebras and the coloring theorem.
But we all know that that SL3 leaves inside any simple Lie algebra. So I think somehow some properties coming from SL4, if we name them in a good way, should contain all information about SL3. So somehow,
but the question in this case is that somehow the reformulation of the coloring theorems in terms of Lie algebras involves very sort of basis dependent, specific ways in which the Lie algebra behaves, and so it's very combinatorial. It's a very combinatorial question about the Lie algebra that can be solved by pictures. You start with the question about the Lie algebra and you write pictures, and then they solve the problem for you. But unfortunately, it's the properties of the pictures that you want to prove. And there may be another way to think about the combinatorics of Lie algebras unknown to us, which will illuminate this.
Yes, and one more question. Not a question, a remark. Sometimes we have minor closed properties like planarity, and sometimes we have properties which are not minor closed, like the property of being bipartite. And actually, if we consider a graph, which is just a trivalent graph with a Hamiltonian cycle, like a chord diagram, then this chord diagram is planar if and only if we can split chords into two non-intersecting families. We put some side and some other outside. So for some families of graphs, one property, planarity, which is minor closed, is related to another property, by being bipartite, which is not minor closed. And I'm very interested in the question whether we can convert properties which are not minor closed to those which are minor closed. So this is a question I'm interested in since a long ago.
Yeah, thank you. That's a very interesting question.
Okay, it has been a great pleasure of mine to listen to your talk. We will be very happy anytime at any seminar, and I really enjoyed it. Thank you very much.
Thank you, Vasily.
Bye.
Goodbye.